Hey everybody, Luke McElroy from Men's Performance Consulting. I wanted to jump on today and have a chat about the fatiguing byproducts of the ATP-PC system and the anaerobic glycolysis system. We'll start off today by talking about the ATP-PC system and how inorganic phosphate creates fatigue. At the end of the day, all we need to understand is that inorganic phosphate will reduce muscular force, and that's the reason why we start to slow down after about 6 seconds into a 100-meter sprint. But I want to talk about how inorganic phosphate reduces that force in a little bit more detail so we have a deeper understanding of how it causes fatigue. Bear with me with my drawings. I'm obviously not an artist. Over here we have a whole muscle. So say this is your calf muscle, for example. All these little lines are one muscle fibre. If we blow that up, this is one muscle fibre here zoomed in. And we'll notice there's a few things going on with this picture. First and foremost, we have actin and myosin. Actin and myosin are basically the contractile components of a muscle. They work together and contract the muscle to reduce force, to produce force. What we've got here, these circles are called myosin binding sites. So actin is going to bind to myosin, or myosin is going to bind to actin, and then they're going to produce force once they are connected. Think of this like a rower. All right, if we want to row, we want to have, if we have only 2 people rowing and 2 oars in the water, we're going to produce some force, but not that much. If we can have 3, 4, 5, 6, 7, 8, 9, 10, 11 rowers, we're going to produce a lot more force than if we have 2. Okay, so we want the myosin to bind to the actin so they can produce as much force as possible. This little line that's covering the holes at the moment, that's called tropomyosin. Okay, think of it as a rope. Basically, all it is, it's covering the binding site. If it's covered, we can't get myosin to bind to actin, so they're not going to produce force. So we actually need to shift this tropomyosin so we can create muscular force. And this is where calcium comes into play. Okay, so this is to do with the power stroke of the cross-bridge cycle, but what happens is calcium gets released from a place called the sarcoplasmic reticulum. It's not important. All it means is that a bit of the muscle is going to release calcium. When calcium arrives at the muscle fiber, at the actin and the myosin, it's going to stimulate, it's going to make this rope move, essentially. Okay, this rope is now going to be stimulated to move off the actin, and now our myosin binding sites are exposed. So what this means is, now that calcium's been released, this has been shifted, now we can get our myosin to connect up to these binding sites. Okay, so now we have 11 rowers, oars in the water, producing a lot of force. This is good. This is how a muscle contracts. In theory, what should happen is the calcium should do that, move the tropomyosin, we contract the muscle, the calcium goes back to this sarcoplasmic reticulum, and then it recycles and goes again and continues to do that to produce muscular force. Now, when inorganic phosphate builds up, what actually happens is it interferes. There's 2 things. It's double negative. 2 things that happen. One thing that it does is that it will actually compete with the myosin binding sites. So what will happen is, I'm writing PI, so inorganic phosphate, PI. They're actually going to fill up those myosin binding sites. So what that means is we have a build-up of inorganic phosphate, and they're taking out a few of those ores from the water. So now we've only got 1, 2, 3, 4, 5, 6 myosin binding sites exposed, which the myosin can then bind to actin. But these PI are blocking up the rest of them. So what's going to happen is we're actually going to produce half the force because half of our myosin binding sites are already taken in by PI. What the PI will do is it's actually going to trap the calcium inside the binding site. So we want calcium to quickly go in, move the rope, the myosin binds to actin, and we contract. But what's happening is these PI are basically catching the calcium and not letting them go back to the sarcoplasmic reticulum. 2 reasons why this is bad. One is because the calcium's already done its job. It needs to go back to the sarcoplasmic reticulum to be recycled. Think of it like a relay race, okay? We're not going to send more calcium to the muscle until the calcium that's already in the muscle goes back, all right? So his partner's basically waiting at the sarcoplasmic reticulum to come and do its job. But because the PI is keeping the calcium stuck in the binding site, it can't go back to the sarcoplasmic reticulum to send more calcium to start contracting again. So basically what inorganic phosphate does is it competes with the myosin binding sites. It fills up the hole. So instead of us having 11 oars in the water, we can only have 5 or 6 as a result. If we can't get calcium back into the muscle, this tropomyosin, this rope, is going to start to come back over the the binding sites, all right? Because we're still getting some calcium release, we're still going to have a few that are available, but it's only going to move the rope partially, and we're going to start to inhibit our ability to move that tropomyosin again. So summary for that, what's happening is, if we look at a muscular force graph, what should happen is our force should peak when we are in a rested state. But what's happening is, because we're getting the calcium isn't being released properly from the sarcoplasmic reticulum, because this inorganic phosphate is stealing the myosin sites, what happens is that we get a reduced muscular force, okay? It doesn't affect the relaxation time of the muscle, but as we can see, we're not producing as much force when we have PI compared to when we're recovered there, and that's how it causes fatigue. Hey everybody, Luke McElroy back again with how hydrogen ions cause fatigue. So obviously hydrogen ions are a byproduct of the anaerobic glycolysis system. So as the byproduct is actually lactic acid, of which we get one lactate molecule and one hydrogen ion. As we know, hydrogen ion is the fatiguing component. Lactate can actually be used as energy. Now, hydrogen is acidic, okay? We've all heard of the pH scale. pH means potential hydrogen. The more hydrogen we have, the more acidic a substance is, okay? So the pH scale is a number from 1 to 14, 14 being very base, very alkaline, 1 being pure acid. Human blood sits between a pH range of 7.35 to 7.45, so slightly on the alkaline side, obviously 7 being neutral, so slightly on the alkaline side. Now what happens is, when we get a build-up of hydrogen ions as a result of using the anaerobic glycolysis system, we're going to push that pH of the blood slightly outside that optimal range. So we might hit, say, 7.25 to 7.3, for example, or outside that optimal range. And what that's going to do is it's going to create muscle acidosis, because our blood is now more acidic than it's used to being. When we get muscle acidosis, we start to inhibit an enzyme called glycolytic enzymes. Okay, so glycolytic enzymes are the enzymes responsible for creating glycolysis. They're found in the mitochondria. When we inhibit glycolysis, obviously we can't create as much energy. Now, a lot of people actually believe that when we have a build-up of hydrogen ions, that it actually affects muscular force, but it actually doesn't, okay? So what happens when we have a build-up of hydrogen ions, the actual force component remains unchanged. What actually happens is that we have an increased muscle relaxation time. So we still produce the same amount of peak force. The muscle just takes longer to come back to a resting length and a resting state. As a result, it is going to change power. Obviously, we know power being speed and strength, or force and speed. So the force component is unchanged, but the length of time and the speed component has been lengthened. So if this was, say, let's just make up a number, 100 newtons of force, and this was 1 second, the force is still 100 with a build-up of hydrogen ions, but it might take 2 seconds to recover, okay? So that would mean that 100 times by 1, or 100 divided by 1 is still, 100 watts, whereas 100 divided by 2 is only 50 watts. So we're actually producing less power, but the force component is unchanged. It's just that the muscle takes longer to relax. The muscle cannot, we know with reciprocal inhibition, the muscle cannot contract while it's relaxing. So if it's taking longer to relax, we can't contract again until it's fully relaxed there. And that's where it comes into play, where we do things like bicarbonate loading, because bicarbonate is obviously a high pH, so more base. If we do bicarb loading, what we can do is we can actually get our blood pH right on the 7.45 stage, so getting it right closer to that base time, that base number. So then when we start to use that anaerobic glycolysis system, it takes longer for us to drop below that 7.35 range. So it's really, really beneficial for sports lasting 8 minutes and less, because they're going to produce a lot of lactic acid, but the science shows that up to 8 minutes bicarb loading is quite effective. Beyond that, it doesn't really matter, because your muscles can only fight off that 7.45 for so long before it drops out below that 7.35 range.